Okay, we're going to take a little bit of a look at what quadratic functions are good for. Now, we've talked about quadratic functions. We've learned to graph them. But you probably saw the video where we did this, but just let's look at it again. Got a uniform cylinder filled with water, and then release it. And the stream is going to go out here, and it's going to cross top of this container. And if you watch where it crosses, it's going to move backwards at a constant speed. The point where it crosses will move backwards at a constant speed. That's a linear function, and we use that as a basis for understanding some graphs of linear functions, best fit graphs, and so forth. The depth of water from the hole up to from the surface down to the hole is going to be decreasing. Is that going to be a linear function? Well, it turns out that's a quadratic function. Now, we're not going to take data and study that right now, but we might later. So I'm going to just release this thing and just watch how the surface of the water decreases more and more slowly as the distance the water stream travels decreases at a linear rate. Stops. Press the water in here. And then put all this aside. So what I'm claiming is that, okay, here's one example. We'll let y stand for the depth and t the time. Now we measure time probably in seconds here. We start at some depth and we decrease until the depth is zero. It's not a straight line graph because you saw that the depth was decreasing more quickly at the beginning than at the end. And if you didn't see that, you can always look back at the video. Just replay that part of the video. I'm going to have a curve that looks something like this. And it stops here. Now, for the sake of students in my section, I'm going to put a red dot here, and that's a standard notation we use for the vertex of a parabola. And of course, this function goes on, but only this part of it corresponds to the reality. This part doesn't occur in reality, although it's part of the function. And the part above this point, this thing keeps going forever in both directions, but it's only on this limited domain. Okay, on the limited domain from t equals 0, we'll say, up to the point where the water flow stops. Only on that domain does a quadratic function model the depth of water in that container. Now, that's, I think, kind of interesting. I could go on and why that sort of thing is important, but we'll talk about that later. Now, there's another model, and it's a very common model, and it's one that I think pretty much every textbook will talk about. And there's a lot of insight to be gained from this model. So I'm going to sketch another graph here. On the x-axis, I've got what I'll call selling price. On the y-axis, except I'm not sure I want to use y here. Okay, so what's going to go on this axis is how many people are going to buy it. Okay, so I'm going to call this D. Demand. The demand is how much people want it, as measured by how many people will actually buy it. Now, let's say you're running a business, and you know if you set your selling price here, and I'm not going to put numbers in this just yet, but if you set your selling price here, you're going to have a certain demand. If you increase your selling price, you expect that your demand is going to go down somewhat. So for the selling price, I'm not going to label, but for the selling price indicated by this vertical line, where the selling price is always the same on this vertical line, and by this vertical line, another selling price. The selling price as the selling price goes up, the demand goes down because fewer people can afford it, fewer people think it's worth the price. Maybe there's a competitor and suddenly find that they can get it cheaper from some competitor. So it makes sense that demand should go down with selling price. Now, that's not always the case. Sell something too low, people might think it's cheap and worthless and not buy it. So, there are subtleties in how demand goes with selling price, but we're going to ignore those and we're just going to pretend that, the demand is a linear function of the selling price. So we assume that demand is a linear function of selling price. So now we can draw a straight line through these points, kind of straight, okay? And say, well, the line really shouldn't extend beyond the vertical axis because your selling price is not going to be less than zero, except maybe in some circumstance where you pay people to take the thing, okay? There's circumstances in which that might happen. When you're stuck with a bunch of them, you got to get rid of them. Maybe you give them away. Maybe you pay somebody a little bit to cart them off. But that's not really going to be part of this model. Okay, so right here we have a linear function, and it's like a y equals mx plus b. But in this case, it's d equals mx plus b, because it's a demand function. Okay. Now, question is, how much money do you take in? Do you take in more money here, or do you take in more money here? So what we have to do with this demand function is we have to determine if you're going to sell this many, mx plus b, how much money you're going to get. And revenue is how many you sell, divided by how much you charge. Or R equals X multiplied by D. X is your selling price. That's how much you charge. D is your demand, which is MX plus B. Okay? So this is how much you charge. This is how many you're going to sell. That's how much revenue you're going to take in. Well, that equals X multiplied by MX plus B. And by the distributive law, X times MX plus, well, X times the quantity MX plus B equals X times MX plus X times B, which is MX squared plus BX. So there's a quadratic function that gives you your demand. Now, you're used to saying quadratic functions in the form AX squared plus BX plus C. Okay? So for that reason, I'm going to change M to A. The demand's going to be AX plus B. Now, the number in front of X is always the slope of a linear function. So now the slope is A. And I'm just making that change because it's going to make what we get here a little easier to look at. Wanted to start out using M, so we're sure that we're saying standard linear function, but now we have AX squared plus BX. Now, you're used to AX squared plus BX plus C, but this is a quadratic function. With C equals 0. What does the graph of this function look like? See if we can sketch its graph. At least see what the graph looks like, get an idea of how we sketch it, and then we'll do an example with some numbers. Okay? So we have I'll write the plus 0 there just so you can see the form of the quadratic function. What's the quadratic formula tell us? It says R equals 0 if X is negative B plus or minus the square root of B squared minus 4AC. All that divided by 2A. In this case, C is 0. If C is 0, then since C is being multiplied by 4A, 4AC is going to be 0. So I'm just going to put a little arrow through that saying that that's 0. So this is just negative B plus or minus the square root of B squared over 2A. And of course, the square root of B squared is just B, so it's negative B plus or minus B divided by 2A. Well, that equals B, negative B plus B over 2A, or negative B minus B over 2A. this equals 0, or, well, b minus b is negative 2b over not 2b, no, over 2a, which is negative b over a. Just to remind you that we can use the quadratic formula to determine when the graph of the function is 0. Now remember, it looks like you've got a negative number here, right? Negative b over a. But remember what a is. Okay, b is a positive number. Why? Because b is the y-intercept of this graph, and the y-intercept is positive. A is the slope. This is a demand function. It goes down as the selling price goes up, and it's clear just from the graph that the slope is negative. So A is going to be a negative number. So that even though negative b over a looks like it should be a negative number, it's a positive number. Well, this is starting to tell us things about the graph. Okay. This function has value 0 when x equals 0. Well, there's the point 0, 0 then. If x is 0, r is 0, so you have the point 0, 0. It's also 0 if x equals negative b over a. Now we've seen that negative b over a is a negative of a positive number over a negative number. So it's going to be a positive number. So negative b over a is here. That negative sign kind of got lost. Let's make it a little bigger. Negative b over a, 0. That's this point. This point, of course, is the origin 0, 0. Now, since a is less than 0, we know that this quadratic function is kind of upside down. It's inverted. Okay, since a is less than 0, if you go back to transformations, you start out with the toolkit parabola, toolkit squaring function, and then maybe you vertically stretch it by factor a. And I'm not sure why I'm drawing those lines. Those vertical lines, at least. Here's your horizontal line. And you vertically stretch it, so maybe it gets a little steeper. And then what do you have to do? Since a is negative, you've got to flip it across the y-axis. So this gives you a function that's going to look like this. Okay, it's going to look like this, but where's the axis of symmetry? The axis of symmetry is that x equals negative b over 2a. You read that off of the quadratic formula, right there it is. X equals negative b over 2a. Notice you have a 0 when x equals negative b over a. Well, negative b over 2a is 1/2 of negative b over a. So that negative b over 2a is going to be halfway between negative b over a and 0. That's going to be here. Here's the line. X equals negative b over 2a. the vertex of the parabola is going to lie on this line. If we plug x equals negative b over 2a back into the form of the function, we can find what r is going to be when x equals negative b over 2a. But the one thing we know is that the graph is going to look something like this. Okay, symmetric, and I went down too fast here. My symmetry is not good in my picture. And I think my halfway point was maybe a little closer to here than it was to here. So in any case, this is, got x here, and you got r, which is revenue, r on this axis, and that's a quadratic function. And that's a pretty standard model used in business. Now, you can also have a cost function. Okay, this isn't profit, this is revenue. And I'm not going to talk about the cost function, but generally the cost function is another linear function. The more of these things you sell, the more of them you got to make. So you say, okay, well, the more I got to make, the more it's going to cost me. And let's assume that's a linear function like this. And then we've got to add that linear function in here, and that's going to change these parameters. Okay, it's going to change the value of A, B, and C. It's going to change the coefficient of x squared. It's going to change the coefficient of x. It's going to change coefficients or the number C. Actually, it's probably not going to change A, but we're not going to worry about that. That's the picture. Now let's work out a quick example. So let's say we have knowledge that from experience we know the X is in dollars, D is in units. If we charge this many dollars, we're going to sell this many. Okay, so let's call this, well, let's just say this is X equals 5, selling for $5. This is our demand, and this is where, let's say D equals 5,000. Okay, now we know if we charge $9, our demand goes down to, let's just say D equals 3,500. Well, now, from these 2 points, we can assume that there's a straight line demand function. Now, that's not always the case, but it's our first assumption. We often assume linearity and then see if linearity really applies. So let's say there's our curve. Well, we can easily find the slope of this curve. And I'm going to assume everybody knows at this point how to find slope. But I'm going to picture it on the graph. Here's my rise. Here's my run. Rise equals 3,500 minus 5,000 equals negative 1,500. This chalk is not writing real clearly, and I'm not helping it, I don't think. But here's your rise. And your run equals 9 minus 5 equals 4. And I'm going to say what that is, 4 units, or $4, sorry. And negative 1,500 units. So your slope equals rise divided by run equals negative 1,500 units divided by $4. Which is negative 375 units over dollars, or units per dollar. So for every dollar extra you charge, you're selling 375 fewer units. Well, the equation we'll use y equals mx plus b. With m equal negative 375, remember that that's units per dollar. And let y equal what it is at either of these points. Let's just take the leftmost point. I'm using y because I'm kind of used to it, but let's call it d. D equals 5,000. And x equals 5. Because when x equals 5, d equals 5,000. We get then 5,000 equals negative 375x. And it's not 375x because x is 5. Okay, so I plugged in m equals negative 375, x equals 5 is here, and b equals 500. There's d, there's 500. We solve this equation. Well, 5 times 375 is 1,875. So I'm going to say b equals 6,875. So our demand function is minus 375x plus 6,875. This is assuming I did my arithmetic right. I'm not going to check it. You can check it for me. And I wrote 355 when it's obviously 375, and I said 375. My hand wanted to do what it wanted to do. Okay, well, there's D. Now, what we're interested in first is our revenue function. Revenue equals the number we sell, which is X, multiplied by how many we sell, which is what D tells us. So this is negative 375x squared plus 6,875 times x, using the distributive law, of course. Okay, well, let's take that function. This is quadratic. A equals negative 375. B equals 6875. C equals 0. So zeros. Now I'm going to skip writing out the quadratic formula, which we should be familiar with by this point. It's going to be negative b, which is negative 6875, plus or minus the square root of b squared, which is negative 375, squared, minus 4 times 6875 times 0, all divided by 2 times negative 375. Now, 4 times 6875, that's 24. That's close to 27,500, I think. But it doesn't matter what it is. You're going to multiply by 0, and you're going to get 0 here. So that equals negative 6875 plus or minus the square root of. Okay, now you've got me stuck squaring 375. That's a little bit of a problem to get that accurate. Now, 300 is close to 400, so that ought to be 160,000, but this 3 would be 90,375. I'm just going to guess and say this is 140,000. All this divided by negative 750, which is what you get when you double 375. So everybody knows what the square root of 14,000 is. If that's right, then square root of whatever we get when we square 375 is 375. Which equals then, I'm running out of time. I am out of time. There's my class. Come on in. I'm going to finish this up real quick. If I add this to this, I get 7,250. And this is then approximately equal to, well, it is equal to 9 2/3. I could now graph this function, but we're out of time. I'll just notice that 9 2/3 is a little more than 9. So we actually want to drop our price down a little bit below $5. Reason being, we're going to sell a lot more. And we're not going to sell as many. We're going to make more money from what we sell. Now, I could have an error here. That seems a little extreme, but of course, this is where the zeros are. This is where we get zero profit. Okay, unfortunately, I can't go on with this, but you can see how the specific demand function leads to a quadratic revenue function. And there's an OR here. It would be OR negative 6,500 over negative 750, which is approximately equal to 8 2/3. No. Yeah. No, it's 8 1/3. Question mark. I'm not sure that's right. Okay, so when I said we're going to lower our price, that wasn't quite accurate. I was misinterpreting what I was calculating. I'm calculating when this thing is 0. Turns out that if these numbers are right, and you go ahead and graph this function, the peak is going to occur at x equals 9, just coincidentally. And that's just a coincidence of the model. But there it is. We're on snow schedule today, snow delay. So I'm sorry, we're out of time. I might come back to this a little bit later and append the rest of the solution.